All right, guys. So in this section, we're going to be talking about what are called two-way tables and tree diagrams. We're going to look at the difference between those two and how they can be very useful when we're wanting to find probabilities. So we're going to start with what's called a two-way table. So a two-way table is a data table that displays data for two different variables. So the reason it's called a two-way table is you've got two different variables that you're looking at. There is such a thing as three-way tables. You can think about that instead of being in a data table as almost like a cube that you would use to represent the data. Obviously, that's quite a bit beyond what we're doing in this class. We're focused mostly on just kind of the basics, so we're just going to look at two-way tables. So let's look at an example of kind of what these look like and how they work. So in order to do that, what is the relationship between educational achievement and home ownership? A random sample of 500 people who participated in the most recent census were chosen. Each member of that sample was identified as either a high school graduate or not, and as a homeowner or not. Overall, we had 340 that were homeowners, 310 that were high school graduates, and 221 that were both. So let's go ahead and display this in a two-way table. Now, when you make a two-way table, most of the ones that we are going to be working with are going to be 3 columns and 3 rows. So let's go ahead and create that now. We've got 3 rows, and here are our 3 columns. Okay, now for our labels, we're going to look at 2 different variables. We wanted to know the difference between homeowners and high school graduates. I'm going to use homeowners at the top here, so H for homeowners, H complement for not homeowners. And then I'm going to use high school graduates. I'm just going to call those graduates and not graduates as graduates complement. So the third spot is for our total. So our total number for each of those is going to be our last part of the table. So let's start filling in some information. We started by finding out that we had 500 total people in the sample. So the total of all of our totals in the bottom right-hand corner is going to have to be 500. The next number we were given is that there were 340 homeowners. So our total number of homeowners, so homeowners going down to the total, is going to be 340. Next, we were told 310 were high school graduates, so graduates total going into this spot is going to have to be 310. Finally, we were told that 221 were both, so if you look for where homeowners and graduates overlap, that's going to be where we'll put 221. Now it just comes down to some basic math to figure out the rest of these values. All of them have to add up. So let's maybe start by taking a look at the 340 and the 500. So 340 plus what number is 500? Well, if you take 500 minus 340, that's 160. We could do the same thing in our third column. So 500 minus 310 must be 190. And then if we continue to do that, let's look at the homeowners column. So 340 minus 221 would be 119. And then for the graduates row, 310 minus 221 is 89. And then at this point, it really doesn't matter whether you want to pick to go down your column or across your row. But if you take, let's say, 160 minus 89, that is 71. And actually, if you wanted to check, 171 plus, or 119 plus 71, does that equal 190? And in fact, it does. So we must have gotten that right. Okay, so now that we've got our two-way table filled out, let's look to see how we can use it to find some probabilities. So suppose we chose a member of our sample at random. What is the probability that the member is, in part B, a high school graduate? So we want to know what is the probability that they're a graduate. I'm going to write that as the probability of G. Well, in order for G to happen, there were 310 total high school graduates out of the total, which is 500. And actually, I would be okay if you left that as your probability. So 310 over 500 would work. If you wanted to convert that to a decimal, as a decimal, that would become 0.62. That would also be an acceptable answer. Okay, let's go ahead and do C. So what is the probability that they're a high school graduate and they own a home? So graduate and a homeowner. What and means, and I think we talked about this, is it actually means the intersection. So really what you want to look for is where do homeowners and high school graduates intersect? Well, here's homeowners and here's high school graduates. And where they intersect is at this spot right here. So this is the spot, and you probably could have found that without looking for where they overlapped. You could have just thought about where does graduates and homeowners both happen. That is the 221 out of the 500. And again, if you want to leave it as that, that's okay. If you want to change it to a decimal, that ends up being 0.442. Okay, so let's go ahead and take a look at some more examples of this. According to the National Center for Health Statistics, in December 2012, 60% of U.S. households had a traditional landline telephone. So these would be the telephones that would have been on your wall or, somewhere on the countertop. And remember, this is 2012, so about 8 years ago. Quite a bit more people still had those. 89% of households had cell phones already, which, again, not surprising. It's 2012. 51% had both. Supposedly randomly selected a household in December 2012. And we're going to make a two-way table that displays the sample space for this chance process. Okay, so for our two-way table, let's go ahead and draw that in. We've got our 3 columns, our 3 rows. We're comparing those that had a landline phone with those who had a cell phone. So I'm going to call that landline and landline complement, cell phone and cell phone complement. And then remember that the last row and last column are for the totals. Okay, so now let's go through and pick out the information that we need. It said that 60% had a traditional landline phone, so our total number for our landlines was 60%. 89% then is our next part of information, and that was that 89% had cell phones, so our total number for our cell phones would be 89. Now, it also mentioned that 51% had both, so 51 had both a cell phone and a landline, so where those two meet, that would have to be 51. Okay, that's all the information we were given so far, so let's fill in whatever else we can. Let's see, going down the landline, so that first column, 51 plus 9 would add up to be 60. Going across cell phones, 51 plus 38 would have to be the 89 for cell phones. And remember, you could just subtract 89 minus 51 to get the 38, 60 minus 51 to get the 9. You might notice that there's a problem. There's really nothing else we can fill out at this point. So we need to find at least one more piece of information. And actually, it's nowhere in the problem. This is just one that you have to use your common sense for. Is if we're dealing with percentages, what do all percentages have to add up to be? And that's going to have to be our overall total. Remember, all percentages have to add up to be 100%. So our overall total, what we're going to put in our bottom right corner, was not told to us in the problem. Is just something we had to figure out for ourselves, is that everything has to add up to be 100. Now, from there, we can go ahead and fill out the rest of this table. So let's go down our totals column. 89 plus 11 would add up to be 100. Across our totals row, 60 plus 40 adds up to be 100. And then that middle spot is going to have to be a 2. That way 9 plus 2 is 11, or 38 plus 2 is 40. Okay, so there's our two-way table. In part B, we're going to construct a Venn diagram to represent this same thing. So let's go ahead and see how this Venn diagram compares to what we saw in part A. So I'm going to draw that in. Remember that for our Venn diagrams, we are doing kind of the traditional 2 circles for our Venn diagram. In addition to that, we need to draw a box around those to represent parts of our sample that were not a part of either of those 2 categories. And I'm going to let the left side be landlines, the right circle be cell phones, and we'll go ahead and fill this out. Okay, so let's maybe figure out kind of the overlap first. So the people that had both a landline and a cell phone, we already know was 51 from our table, so that would be 51 right here. Then if you think about it, those that had a landline but not a cell phone, so the spot right here, that's going to be landline but not a cell phone, is going to be the 9 from our table. Next, let's fill in those that had a cell phone but not a landline. So cell phone but no landline is going to be the 38 that was right in our table there. And lastly, we need to know those that had not a landline nor a cell phone. That's going to be this 2% that's going to go out here. So notice that the only numbers we're using for our Venn diagram are those in this top left portion of our table. In other words, we are not using the totals at all when we're constructing our Venn diagram. Okay, so now let's go ahead and answer some questions. For part C, it wants us to find what is the probability that the household has neither type of phone. So that would be the probability that they don't have a landline, so landline complement, and they don't have a cell phone, and cell phone complement. You can find that two different ways. You can find that in the table, so landline complement and cell phone complement is the 2% right there. Also, that would be this 2% that's outside the two circles of our Venn diagram. For part D, find the probability that the household has a cell phone only, so that they have a cell phone and that they don't have a landline. So a cell phone and landline complement. So that would be C and LC. So C and LC in our table would be this 38%. Or you could use your Venn diagram and look for where are the cell phones without landlines, and that would be the 38% right here. Okay, let's go ahead and skip this next example. If you want to work through it, that's more than okay. It's just another example of constructing a two-way table, but I'm going to skip over it for right now. Let's go ahead then and move on to tree diagrams and see how these are a little bit different from two-way tables. So, tree diagrams are useful for showing conditional probabilities. In other words, conditional probabilities is where one event happens and then that helps to determine the next event. And so what we're going to do is we're going to use paths or branches, if you want to think about them for a tree, to show kind of the different outcomes that are possible. So let's take a look at an example of this. We've got Shannon, and let's say Shannon hits the snooze bar on her alarm clock on 60% of school days. If she doesn't hit the snooze bar, there's a 90% chance that she makes it to class on time. However, if she hits the snooze bar, there's only a 10% probability that she makes it to class on time. Let's go ahead and make a tree diagram to represent this situation. In order to do so, we need to think about the two events that are happening. The first event is that she's either going to hit her snooze bar or not. The second event is she's either going to make it to class on time or not. So let's go ahead and think about which one comes first. And I would hope that we can all agree that the snooze bar is what's going to happen first. So either we're going to hit the snooze or we're not going to hit the snooze. Now, it says that she hits the snooze bar on 60% of her school days. I'm going to write that as a decimal 0.6. That means that she does not hit the snooze bar on 40% of school days, so I'm going to write that as 0.4. Okay, so once she hits the snooze bar, this next event that we're going to look at is whether she makes it to class on time or not. So that would be that she's either on time or that she's late. And we're going to do that for each of the two scenarios where she's either hitting the snooze button or not hitting the snooze button. Now, it says if she does not hit the snooze bar, there's a 90% chance that she makes it to class on time. So that would be that we'll follow the no snooze path and the on time path. And it says that that's going to happen 90% of the time. That means that the remaining 10% of the time she's going to be late. However, if she hits the snooze bar, there's only a 70% probability that she makes it to class on time. So if we follow snooze bar on time, that's only 70% of the time. That means the remaining 30% of the time, she's going to be late to class. Now, it's also useful to find the combined probabilities for each of these happening. What I mean by combined probabilities is what is the probability that she hits the snooze bar and is on time? And in order to find that, what we need to do is multiply the two numbers that it takes to get there. In other words, multiply 0.6 by 0.7, and that ends up multiplying to be 0.42. In other words, she's going to be on time if she hits the snooze bar 42% of the time. Whereas being late, if we take 0.6 multiplied by 0.3, that ends up being 0.18. So she's going to be late 18% of the time when she's going to school and hits the snooze bar. If we continue to do that, we'll find that the probability here is 0.36 and that the probability here is 0.04. And in fact, if you were to go through and add those up, you're going to end up adding up to be 100% for all of our probabilities. Now, it doesn't ask us for it in the problem, but let's just say we wanted to find the probability that she was late to class. Well, there's two different scenarios where she's late. There's where she hits the snooze bar and is late, and where she doesn't hit the snooze bar and is late. The first path is 18%. The second path is 4%. So if we wanted to know the probability that she was late to class, 0.18 plus 0.04 is 0.22. So she's going to be late 22% of the time going to school. Let's just do one more example of setting up a tree diagram, and that'll be it for this video. So many employers require prospective employees to take a drug test. A positive result on the test indicates that the prospective employee uses illegal drugs. However, not all people who test positive actually use drugs. Suppose that 4% of prospective employees use drugs. The false positive ratio is 5%, and false negative is 10%. And we're going to use a tree diagram to represent this scenario. So let's think about the two things that are going to happen. We're going to have the employee who's either going to be taking drugs or not taking drugs. And then we're going to have the test results. And again, which one's going to happen first? Well, the drug use is going to happen before the test results happen. So that's going to be how we'll start our tree diagram. Is we're going to have the prospective employees who use drugs and those who do not use drugs. So it tells us that 4% of prospective employees use drugs, so 0.04 use drugs. That would leave 96% to not use drugs. Now, in addition to that, we're going to have people who test positive for drugs and those who test negative for drugs, as well as for those who do not use drugs. Now we just need to figure out what does it mean to be false positive and what does it mean to be false negative. So a false positive would be someone who does not use drugs and still tests positive. So someone that's not using drugs and still tests positive. So this pathway right here, it tells us that the probability of that happening is 5%. That leaves 95% to test negative, assuming they're not using drugs, which is good. That means that it's 95% effective when they're not using drugs. Now let's go ahead and find the false negative. So false negative is that they're using drugs and still test negative. And it tells us that that happens 10% of the time. That leaves us with a remaining 90% of the time that if someone's using drugs, they actually test positive using the test results. Okay, so now let's find our combined probabilities. In other words, the probabilities of them happening both at the same time. So the probability that they use drugs and then test positive, we're taking 0.04 multiplied by 0.90, and that ends up being 0.036. Next, we'll do it with 0.04 multiplied by 0.10, and that ends up being 0.004. And then if we continue to do that, 0.96 multiplied by 0.05 is 0.048. And 0.96 multiplied by 0.95 is 0.912. So let's say we maybe wanted to find what is the probability that a employee tests positive. So the probability that they test positive, that can happen two different ways, that they're using drugs and testing positive, or that they're not using drugs and testing positive. So that would be the 0.036 and the 0.048. And if we add those together, we get 0.084. In other words, there's about an 8.4% chance that the test comes back positive. Only about half of those are going to be accurate if you think about it, though. Only about 0.36 out of 0.084 only about 50% of those positive results are actually positive. So that's why what you'll oftentimes see with drug testing is if someone tests positive, they're usually given another test to confirm those results rather than just going based off the results of one test. All right, guys, that's all I've got for you in this video. Until next time, have a great day.